Good afternoon, Internet. I am Matt Buyak, and in this video we will solve the 10th problem from the Project Euler Problem Archive. So this is basically the cherry on top of my primes series, which we just finished. In particular, the primes class that we wrote as part of that series is going to make this problem trivial. You'll see it asks us to find the sum of all primes less than 2 million. So let's get into it. Now, before we start writing any actual code, we'll need to make a minor change to our template directory, and in particular in the make file. You'll recall that our primes class lives in our libnumtheory library, and so we'll need to be sure to link that in our make file here. So let's copy that from our primes test here, and in particular the make file from that directory. So we want to set our include directory, our libraries directory. For now, let's not link libnumtheory. We may not need that for every problem. So just for our template directory, we'll leave those out of it. So we'll just add our include and library directories like so. And now we're ready to create our problem directory. So we'll copy our template to problem 010. We'll see we're in double digits now. And let's open up our corresponding main.cpp. So as I mentioned, we will still need to modify the make file specifically for this problem to link our libnumtheory here. We'll also need to include primes.h. OK, now we should be ready to get started. So we'll need an upper bound for our search. So we'll say uint32t n. Let's make that static and constant. And we'll set that to 10 to start. You may have noticed that they give a sample input for the sum of primes below 10. So we'll start with that also. Next, we'll need our primes object. So we'll say primes pointer p is equal to new primes. At the end of our function, we will delete that. We will need an index I and a variable for keeping track of our sum. You'll notice I specifically used a 64-bit integer here. We can expect adding up the primes less than 2 million that we're probably talking about, tens of thousands or maybe even over 100,000 primes. And so we very likely will break the 4 billion mark for our sum, which is the largest value that can be stored in a 32-bit integer. So we're using 64-bit integer just to be certain. All right, so now we'll say I is equal to 0, and we want p get prime I is less than n, and increment I, and we'll say sum plus equals p get prime I. Oh, we need to initialize our sum to 0, and we'll need to print our sum equals sum. OK. One thing to comment on briefly, this may look wasteful to call this get prime twice. which it might be if we were actually calculating the prime every time, but you'll recall that the way our primes class works, if we just jump over to that real quick, is that we only do calculations if we have to grow the size of our list of primes. If we already have the primes that we're looking for, then we just return them directly. And so it's not wasteful to call this twice. That should be fine. Okay, so now let's head over to our common directory and rebuild that. Head over to our problem directory and build that. Run our solver. We see the answer is 17, which matches the test input there. And so now we'll ramp this up to 2 million and see what we get. All right, that finished pretty quickly. That's always satisfying. And you'll see our answer there. It looks like 142 billion or so. Now let's check in the archive. And you'll see that our answer matches. Now you may notice that this is one of the quickest solves that we've had so far. And in large part, that's because of the primes class that we spent so much time on. So this really goes to show that if you have the right supporting classes, you can really make some of these problems a lot easier. And so the time that we spent on that was certainly a good investment. So that's it for this video, and for the next video, we'll continue with problem number 11.